this is Whitney here. We're going to be talking today about significant figures, or as you'll hear them referred to over the course of the next year, sig figs. Um, and these are playing into the activities that you did earlier today or last week or whatever it may be, where you were looking at different degrees of accuracy in measuring and also figuring out, how many digits you can actually estimate when you're making a measurement. So significant figures are going to play into this. And you might be wondering, what is a significant figure? These are also referred to as significant digits, but sig figs sounds cooler than sig digs, so that's why we call them that. But what are they? So this is the number of digits that are in a value, often a measurement, that contribute to the degree of accuracy of the value. So what on earth does that mean? Well, if I were to ask you, how old are you? You might say, oh, I'm in my teens. I mean, you probably wouldn't say that, but you might. And some of you might say, oh, I'm 16, which we all know means that you might actually be almost 16, but you're actually 15 and you're just rounding. Or you could say, I'm 16.08 years, which means you're 16 in 1 month. So each of these values has a different degree of accuracy, and because of that, also has a different number of significant figures in the value. So we have a set of rules that I'm going to walk through with you about significant figures, and you'll also get a chance to try out some questions on your own. So our very first rule is that all non-zero digits are significant. So this is any number 1 through 9. Anytime you see a number 1 through 9, that means that it is a significant digit. So for example, here, the number 12 has 2 non-zero digits. So this number has 2 significant digits. Here, 5,282, these are all non-zero digits. So that means that this number has 4 significant digits. Now I know you're probably thinking, okay, but what about zeros? And the next 3 rules are all about zeros. So let's see what our next rule is. Well, the next rule is that all zeros between non-zero digits are significant. So for example, we have this number here, 505, and there is a 0 in between 2 non-zero digits. That means that this 0 is significant because it's in between 2 other significant digits. So that means that this number here has 3 significant digits. Over here we have 6,000,008. And even though we have all these zeros here in the middle, the fact that they are in between a 6 and an 8, which are both non-zero digits, means that in this number we have 1, 2, 3, 4, 5, 6, 7 significant digits. So let's pause before we talk about the rest of our rules and see if you can answer these 2 questions. All right, so hopefully you took a look at this and you said, you know what, there are no zeros in that number. It is just non-zero digits. This number has 4 significant digits. And over here, this number, 6,066,897, every single one of these is significant. So that means we have 7 significant digits. Okay, what about our other 2 rules about zeros? Let's see. So rule number 3 is that zeros to the left of a non-zero digit are not significant. So if we were to look at this number 0.00035, we have 4 zeros that are to the left of non-zero digits. Now these zeros here are just placeholders. They're just telling us to which tenths this measurement is. So in this case, we only have 2 significant digits, the 3 and the 5. Now I know some of you are thinking, but wait a second, 0.00035 is very different from 35, and you're absolutely right. However, we could write this number if we really wanted to in scientific notation, and we would get 3.5 times 10 to the negative fourth. This number here would only have 2 significant digits. We'll talk about that later. That's just in case you were wondering why we're allowed to just ignore these zeros when it comes to estimating significant digits. Over here, we have 0.08906. Again, these zeros are leading zeros, so they are not significant. But what about this other zero, right in between the 9 and the 6? Well, it is in between 2 non-zero digits. These other numbers we know are significant because they are non-zero digits as well. So this number has 4 significant digits. Okay, we got one more rule, and then you'll get to do some practice. The last rule is also about zeros. All zeros to the right of a non-zero digit are only significant if there is a decimal point. So let's take a look at some examples and talk about why this is. For example, down here, 300. This number, because we have a non-zero digit and then 2 zeros in a number without a decimal point, only has 1 significant digit. And that's because in reality, this could be like a rounded number from, say, 314. We don't know. The decimal is what gives us that certainty. So taking a look at this, we have 2.00. We have a decimal and 2 zeros coming after that decimal. And so we are allowed to count these as significant digits, along with our 2, of course. So this number here would actually have 3 significant digits. And last but not least, our final example, 51.250. We know that all of these are indeed significant. This number, however, 0, what do you think? Aha, it comes after the decimal. It's to the right of the decimal, so it is indeed significant. Okay. Now it is your turn. Go ahead and spend some time answering these 6 questions about how many significant figures are in each of these numbers. Okay, if you got all of those correct, feel free to turn this video off. If you missed any of these, I'm going to walk through these with you really fast, so feel free to stick around and see maybe what you got wrong. So in this case, there are 2 non-zero digits, and all of the zeros in this number are coming before the non-zero digit. So this number only has 2 significant digits. Our next question, 30,009. All of these zeros are in between non-zero digits, so all of these are going to count. 1, 2, 3, 4, 5. Our next one, 60,000. Do you see a decimal in this question? Yeah, me neither. Which means that because there's no decimal, none of these zeros are significant. So this number here only has 1 significant digit. This one looks kind of funky, doesn't it? You will actually see this a few times throughout the year because we know, because of this decimal, that this is 1,000 exactly. It's not around 1,000. And that's what this decimal is telling us, that this is exactly 1,000, which is why these zeros are significant. So we have 4 significant digits here. Our next question, we have 2 different types of zeros. There's some that are leading and some that are trailing. These leading zeros are, oopsies, I meant to put that in red, are, oh, come on, pen. These leading zeros, because they're in front of the non-zero digits, these are not significant, but we have a 0 at the end. This is telling us that there's this level of accuracy in this measurement. So we have 3 significant figures in this number. last but not least, we have 3,005,000.00. We know this is exactly 3,005,000.00. So it's not, we have to count these trailing zeros because there's a decimal. These zeros are in between two non-zero digits, so those also count. That means that every single number in this number is a significant digit. So 1, 2, 3, 4, 5, 6, 7, 8, 9 significant digits. I hope this helped and that you now feel like significant digits are fun, because they are. All right. Thanks, everyone. We'll see you next time.